So now that we've discussed units, we've discussed measurements, and we've discussed significant figures, we're going to put them all together to conduct unit conversion, or, as it's sometimes called in chemistry, dimensional analysis. Now, with dimensional analysis, we have some steps that we're going to follow that are going to help us organize our thoughts, organize our problem solving. I highly recommend that you start any problem with these steps until you get used to doing the calculations. Once you get used to doing the calculations, yeah, you can skip some of these steps, but if you ever run into a difficult problem, come back to these steps. They're going to help you stay organized with your thoughts. They're going to help you create a plan of attack for these problems. Also, keep your book handy so you can quickly look up certain unit conversions that you may need. Now, I'm going to go through all this stuff, and I know a majority of you are going to just ignore my advice. That's just the way it goes, it seems. But I'm going to beg you, please try these steps out. Listen to what I'm going to talk about in this presentation. Listen to the tips I'm going to give you, especially about units. Learning to follow these things now, they're going to help you out in the long run. Yeah, it may seem like easy problems right now, but when we get to the harder problems, having these concepts down and this general idea and these general steps of how to solve a problem are going to help you out immensely. So please, try to use these steps and try to use the hints that I give you. They're going to help you out. All right, so let's get on to the steps then. So the first thing you're going to want to do whenever you come across a problem is you're going to want to sort the information. You want to write down, and I recommend actually physically writing things down. Write down what information you're given. Make sure you include units with these. Then you want to write down what do you want to find. What's your final answer going to involve? What's your final units going to be? Those are going to be very important. Next, we're going to come up with a strategy on how to solve the problem. First, we're going to come up with a conceptual plan. All right, it's just going to be a basic idea of doing unit conversion. The main thing about this is we're going to think about canceling out units. All of this stuff, it's going to come back to the units. I'm going to emphasize again, you've got to pay attention to units. You've got to write down the units. All right, once we have a conceptual plan, we're going to think about relationships. Now, what do I mean by the relationships? Well, it's mainly what conversion factors I'm going to be able to use. How am I going to get from one unit to another? Once I have that strategy in place, I'm then going to solve the problem. Once I've gone through and solved the problem, I'm going to check my answer to see, does it make sense? If it makes sense, great. If something seems odd, I may have to go back and rethink my strategy and then resolve it again and then check it again. All right, so let's use these steps. We're going to go through an easy problem first. So this first problem, what is the mass in grams of an object that weighs 129 pounds? Well, let's sort the information. That's simple enough. We're given 129 pounds. We want to find the mass of that in grams. So let's come up with a strategy. First, we want to come up with a conceptual plan. We want to go from pounds to grams. All right, simple enough. So relationships. 1 pound is equal to 453.59 grams. Now we want to solve. Now when we go to solve, this is going to be very, very important. Start with the units. Set it up so that the units cancel. If the units are canceling, the numbers are going to go in the right spot and you're going to be able to do the calculation correctly. If you focus just on the numbers, a lot of times you're going to get them confused, put them in the wrong spot, end up with the wrong answers. So make sure to start with the units. Make sure they cancel. Let me show you what I mean by that. We're starting with pounds. You notice under pounds I drew a line and put nothing underneath it. That's just so I know that pounds is in the numerator. Okay. I want to get rid of pounds, so pounds needs to go in the denominator in the next step. Grams then needs to go on top. Now in looking at this then, my pound units are going to cancel. I'm then left with grams. So just based upon the units, I started with pounds, I'm ending with grams, I did what I wanted to. Now, the other thing you may notice is I left some space in front of my pounds, left some space in front of my grams. I did that so I could go back and put the numbers back in to do the calculation. So once I know that my units are going to cancel and I'm ending up with the units I want, I'm going to put the values in. So I've got 129 pounds, I've got 453.59 grams over 1 pound. By writing out those units first, when I look back at the relationship, I know one goes with the pounds and the 453.59 goes with the grams, which means the 453.59 is on top and the 1 is on the bottom in that unit conversion. I don't get confused and have to figure out, am I dividing, am I multiplying, what am I doing? Okay, so write those units out, show them cancel. All right, so when I do that, I end up with a value that's 58,513.11 grams. Now I need to get that to proper significant figures. So I need to go back and look at the values I'm using. Since I'm doing multiplication division, I'm going to end up with an answer that's got the same number of sig figs as my measurements got the fewest number of sig figs. So in 129, that's got 3. The 453.59, that's got 5. And this is where it gets a little bit tricky. The 1 in the 1 pounds there, since it's part of conversion factor, it's actually 1.00000. Anytime you see a 1 that's part of a conversion, it's got infinite number of significant figures. Okay, so that being said then, I'm going to be limited to 3 significant figures. So I'd round that value to 58,500 grams. But now, when somebody looks at that value, they don't know whether those zeros after the 5 are significant or not. So what I need to do in order to indicate to somebody else who's looking at this is to write that in proper scientific notation to avoid that ambiguity. So I'd write 5.85 times 10 to the 4th grams. That tells me I have 3 sig figs. And that would be my final answer. Now the last thing in these steps that I want to do is I want to check my answer. All right, so to check my answer, I can go back through and double check the calculations if I want in my calculator. I can double check to make sure units are canceling properly, make sure I've got numbers in the right place. But one of the easier things to do is just see if it makes sense. All right, so if I start with 129 pounds and for every 1 pound I have 453 grams, well, my answers should end up being a fairly large number, right? Because there's going to be a lot more grams than there would be pounds. Right? So it's that kind of a quick check initially to see, does the answer make sense. If I ended up with 5.85 times 10 to the negative 4th grams, that wouldn't make sense. Why would I end up with a smaller amount of grams than pounds when I know I should be having more grams per pound just based upon that unit conversion between pounds and grams? All right, let's look at a little bit more complicated one. So we're going to convert 226.4 meters per second to miles per hour. So the first thing we want to do is we want to sort our information. So we're given 226.4 meters per second. We want to find miles per hour. So let's come up with a plan. We're actually going to be doing 2 different conversions here. So we're going to think about it in terms of being 2 parts. The first part, we're going to go with the lengths. We're going to convert meters to kilometers to miles. Second part then, we're going to go with the time aspect. We're going to go from seconds to minutes to hours. All right, so for our relationships, let's only think about part 1 at the moment. So 1 mile is 1.6093 kilometers, and there's 1,000 meters in 1 kilometer. So let's solve this problem. Remember, we're going to start with the units and make sure they cancel. This is only part 1. We're starting with meters over seconds. Now I'm only going to worry about converting the meters at this point. So in the next step, I put meters in the denominator. I'm going to put kilometers on top. My meters are going to cancel. If I were to stop the calculation here, I'd end up with kilometers per second. But I don't want kilometers per second, I want actual miles. So I'm going to put kilometers in the bottom of the next step. Miles on top, my kilometers cancel, and now I'm left with miles per second. Let's put in some values here. So I've got 226.4 meters over 1 second times 1 kilometer over 1,000 meters times 1 mile over 1.6093 kilometers. I get an answer of 0.14068822 miles per 1 second. Now I want to consider proper sig figs. So in considering that, I've got my initial measurement, which has 4 sig figs, the 226.4. The 1 kilometer over 1,000 meters, I'm not going to concern myself with. Anytime I have a prefix conversion, don't consider it part of determining number of sig figs. It's really just moving a decimal place around. That's all it's doing. The 1 mile over the 1.6093 kilometers, well, the 1.6093 has 5 sig figs. The 1, just like we talked about before with the pounds and grams, that 1 in the 1 mile has infinite number of sig figs, so we're not going to use it for consideration. So really it comes back to that initial 226.4, which has 4 sig figs. So if we were to stop the calculation here, we go to 0.1406 miles per second. We'd want to put that in proper scientific notation, so 1.406 times 10 to the negative 1 miles per second, and that would be our final answer if we were going to stop there. But this is only part 1. We're still going to check to see, does this make sense? And it does, right? Which is bigger, a meter or a mile? Well, obviously a mile is bigger than a meter, so we should have fewer miles than we do meters per second. Right now, I'm going to continue on to the next part. So I'm going to start with the same information I had before. Right? I've got the same conceptual plan, except now I'm going to deal with part 2. So I'm going to go seconds to minutes to hours. So relationships, 60 seconds equals 1 minute, 60 minutes equals 1 hour. Let me solve. Remember, I'm going to start with units and make sure they cancel. So for part 1, I'm going to have miles over seconds. That's the units I ended up with from part 1. Now, I don't want to convert the miles anymore. I want to get rid of the seconds. So in the next step, seconds go on top, minutes go on the bottom. So my seconds cancel. Now I need to get rid of my minutes. Minutes go on top, hours go on the bottom. So my minutes cancel. And my final units will be miles per hour. Now I'm going to put in the values, and I'm going to use the values from part 1. So I've got the 0.1406. Now, I could carry that whole number through in the calculation. Remember, we talked about rounding error. So I could carry that number from the first part through to this part, as long as I recognize that that number really, for the final determination of sig figs, only has 4 sig figs. So in doing this calculation, I get 506.456 miles per 1 hour. Proper number of sig figs then, well, the 60 seconds per 1 minute and the 60 minutes per 1 hour, those are by definition, so we don't include those values in determining sig figs. So the proper number of sig figs is going to be 4. So I'd end up with 506.5 miles per hour. Need to put that in proper scientific notation, so the 5.065 times 10 to the second miles per hour. That would be my final answer then. Now I want to check to see, does this answer make sense? Well, if I've got 226.4 meters per second is what I started off with, and now I want to go per hour, well, I should end up with roughly real close to about the same amount of miles per hour. So yeah, that seems to make sense. If I'd have gotten a really small value, it wouldn't have made sense, but this one does. All right, let's add a little twist to this. This is going to be a useful tool for you when dealing with units that are squared and cubed. All right, I'm going to show you the example with cubed. So we're going to convert 5.075 millimeters cubed to kilometers cubed. So sort the information. We're given 5.075 millimeters cubed. We're going to find kilometers cubed. Conceptual plan. We're going to go millimeters cubed to meters cubed to kilometers cubed. Anytime you're converting between units that have the same base unit, the best thing to do is to convert initially to that base unit, then back to the next unit. So in this case, meters is really the base unit. So if I go from millimeters cubed to meters cubed, then to kilometers cubed, it's going to be a lot safer than just trying to directly go from millimeters cubed to kilometers cubed. A lot of times when people skip that middle step, they mix up the numbers. Okay? Yes, it's going to add a little bit more to the calculation, but not that much more, and you got a better shot of getting the correct answer by doing it that way. All right, so let's look at the relationships. So 1 millimeter is 1 times 10 to the negative 3 meters. We got 1,000 meters in 1 kilometer. So let's solve it. Remember, once again, starting out with the units. In this case, since I'm starting with millimeters cubed, what I'm going to do is I'm not going to go from millimeters cubed to meters cubed. I'm going to break it up into 3 separate parts. So there's a millimeters cubed on the bottom 3 times. That will cancel out with the millimeters cubed on top. All right. The reason for that is when I put my numbers in, I can see what numbers have to be cubed. Doing it this way makes it a lot easier to see. If I just had millimeters squared, I'd only do it twice. If I had millimeters to the fourth, I'd do it 4 times. Okay, so just showing these units canceling out this way is going to make the calculation a lot easier. All right, so in looking at this, I'm going millimeters cubed to meters cubed in the first part, then meters cubed to kilometers cubed in the second part. You can see on the bottom I've got 3 millimeters. When I take millimeters times millimeters times millimeters, I get millimeters cubed, which will cancel out with my millimeters cubed up there. Now, if I look across the top, if I had just stopped there, I'd have meters times meters times meters, which is meters cubed, but I don't want to stop there. I want to take those to kilometers. So each one of these meters on the bottom in the next step is going to cancel out with a meter in the top in the previous step. And then I'm left with kilometers times kilometers times kilometers, which will be kilometers cubed, which is what I'm going for. So I'm going to put the values in. Start with that 5.075. All right, you can read through all those values. I'm not going to read through them all. But you can see with those values, you're actually cubing those values as well, which is the step that people miss. They'll just say 1,000 meters cubed is equal to 1 kilometer cubed, and that's not true. 1,000 cubed millimeters cubed is equal to 1 kilometer cubed. So writing it out this way makes it easier to see. All right, so we end up with a final answer of 5.075 times 10 to the negative 18 kilometers cubed. So that would be our final answer. Now, does that make sense? Let's check it. Well, would I expect to have a smaller kilometer than I would a millimeter? Sure. If I'm starting with millimeters, that's really small in comparison to a kilometer. So to get those roughly equal, I have to have a really small amount of kilometers. So it makes sense. All right. Another example here, and this is going to give us an important relationship. We have a common volume unit in the medical field is the cc, which is a cubic centimeter. So we have 5 cc's is going to be equivalent to how many liters? So let's sort the information. We're given 5 cc's or cubic centimeters or centimeters cubed. We want to find liters. So we're going to come up with a strategy, our conceptual plan. We're going to take centimeters cubed to milliliters and milliliters to liters. So what are our relationships? 1 centimeter cubed is equal to 1 milliliter. That conversion you absolutely need to know. It's very, very important. And then we're going to take 1,000 milliliters is equal to 1 liter, just a prefix conversion. All right, so let's solve this. We're going to set up our units. Okay, so when we set this up, we can see our centimeters cubed cancel, our milliliters cancel, and we're left with liters. We can put in the values, and we can see that we end up with 5.00 times 10 to the negative 3 liters. Remember, those zeros are significant because they're coming after the decimal place in that first measurement. So the first value, the 5.00, has 3 sig figs, which means our final answer should have 3 sig figs. Right? So that would be our final answer. Now let's check that. Does it make sense? Well, if I start with 5 cc's, which is roughly 5 milliliters, yeah, milliliters is a lot smaller than a liter, so I'd have fewer liters than I would milliliters. All right, another type of conversion where we can consider this is we don't always have a nice, neat unit conversion that we can use, but we do have relationships like these equations here. We have the relationship between Kelvin and degrees Celsius and degrees Fahrenheit and degrees Celsius. Okay, you need to know those equations. More importantly, you need to know how to use them. So, what is 512 degrees Fahrenheit in Kelvin? Let's sort the information. We're given 512 degrees Fahrenheit. We want to find Kelvin. Let's come up with a strategy. First, our conceptual plan. We'll go degrees Fahrenheit to degrees Celsius. Then we'll go degrees Celsius to Kelvin. What are the relationships? Well, we have our degrees Fahrenheit to degrees Celsius equation. We have our Kelvin to degrees Celsius equation. Let's solve this. Now, sometimes in this case, we don't have necessarily a direct unit conversion, but we want to come up with a general idea of how we're going to solve this problem before we worry about the values. Don't get caught up in the values all the time. I know it's important at the end, but initially think about those units. We start with the degrees Fahrenheit to degrees Celsius equation. Since we're starting with degrees Fahrenheit and we want to get to degrees Celsius, we rearrange that equation and we end up with an equation that's degrees Fahrenheit minus 32 times 5 divided by 9 will give us our degrees Celsius. Once we know degrees Celsius, we add 273.15 to it, and that'll give us our Kelvin temperature. Now we put the values in and solve. When we plug in those values, we end up with 266.67 degrees Celsius. Then we take that 266.67 degrees Celsius, add the 273.15, and we get 539.82 Kelvin. We're going to end up with an answer that's going to have 3 significant figures. Actually, more importantly, it's going to have 0 decimal places. So how am I going to get that? Well, if I go back to the 512 minus the 32, 512 minus 32 would give me an answer that has 0 decimal places. Now I've got that 5 divided by 9. That's going to be like one of those prefix conversions. We're not going to include that in your consideration for number of significant figures. So in considering that, the 266.67 should really end up with no significant figures. The 266.67 should end up with 0 decimal places. So when we go to the second calculation, we have 0 decimal places and then something with 2 decimal places. So our final answer should have 0 decimal places. So proper number of sig figs, 3, we should end up with 540 Kelvin. But remember, we got that 0 there, and regardless of that, we should always put it in proper scientific notation. So we'd end up with 5.40 times 10 to the 2 Kelvin. Okay, then we need to check this. Does this make sense? Well, when we think about the Kelvin scale and the Fahrenheit scale, they're always going to be larger values in comparison to the degrees Celsius. So yeah, it seems like it's reasonable. All right, we've gone through several examples. Those examples talk about some key points dealing with unit cancellation, dealing with significant figures, coming up with a plan of attack for these things. Remember, you want to set your problems up where you sort the information, you find out what's given, what you need to find, you strategize then, come up with a conceptual plan, come up with relationships that will allow you to carry out that conceptual plan. You then want to go through and solve. But remember, with your solution, focus first on canceling out the units. Once you're done solving the problem, then you want to check your answer. Now, when you're working problems, it doesn't have to be in this nice, neat table, but you do want to keep things organized. You want to be able to go back and look over what you've done. All right? So really attempt to set your problems up using these rules or these guidelines. And also remember, always pay attention to units. If nothing else, make sure you're setting things up so that you're showing the units cancel before you're trying to do any sort of calculation. In the long run, trust me, it's going to help you. All right? That's the end of our discussion of dimensional analysis, but you're going to use this so much throughout the rest of this course, so make sure you get this information down. And we'll catch you next time.